Assalamualaikum and a very good morning. Today I would like to present about BMMU 4004 Bachelor Degree Project 2. Okay, the title of my project research is Effect of Acoustic Property on COGON Grass Fiber. Before that, let me introduce myself. My name is Amir Haziq bin Anuar. My matric number is B0717105558. My supervisor is TS Matric No bin Osman. Okay, this is table of content of my slide. First, we go to the introduction, background of study. Okay, generally, noise is unwanted sound or tone. Sound is created when objects are vibrating in air. We must now be conscious that there are many ways in which an application can be used to reduce noise levels. There are two ways of controlling noise. First is passive noise control and second is active noise control. The method that we are used in this research is passive noise control, where natural fiber are used as a sound absorber to control the noise. Okay, the problem statement of this research is nowadays synthetic material is used as a sound absorber, where synthetic material can cause global warming, harmful to human health, and also very expensive to get. The other problem statement is preventing COGON grass ending up as a waste. Okay, the objective of this research is to extract fibers from COGON grass, to construct sample of the sound absorber from COGON grass fibers, and to measure the absorption coefficient of the fibers. The scope of this research is the emphasis of this study is to determining the sound absorption efficiency of the COGON grass fiber. The process extracting fibers and making samples will be performed. The parameters that will be observed are the effect of thickness, density, air gap, fabric, and also comparison between synthetic fibers. The parameters that will be controlled are the thickness and the densities of fibers. There will be no binder and compression process on the samples during the research. Other properties of the COGON grass fiber such as structural length, thermal conductivity, and fire retardant are omitted during sound absorption coefficient evaluating. Okay, next we are go to the literature review. Okay, the first author is Zulkifli in 2010. The finding is about the potential of natural fiber in sound absorbent. The coefficient of tone diffusion of natural fibers are proven. Coil fiber can be used as sound absorber. The second author, Lim in 2018, find about the air gap impact, the comparison of different thickness of sample that affect the air gap and coefficient. Okay, next, the author is Azma Putra and Y. Abdullah in 2013. The finding is about the weight ratio, where the effect of varying the composition of other additive blowing agent and filler on the acoustic performance as well as the strength of the panel is also interest. After that, the Wang in 2019 is about the thickness effect. When thickness of the sample increase, the sound absorption coefficient also increase. And lastly is Koizumi in 2002, the effect of density. When density of the fiber increase, the ability of the fiber to absorb sound increasing too. Okay, next we go to methodology. This is the flowchart of project. First, preparation of raw material, extract COGON grass fiber, sample preparation, measurement analysis, and good acoustic performance, and then conclusion. Okay, this is preparation of COGON grass fiber. First is process of boiling COGON grass. The leaf of the COGON grass were cut and placed into aluminum container. 50 liters of water is poured inside to make sure the COGON grass are fully soaked. The fire was turned on and the aluminium container was closed. Left the COGON glass for 4 hours to make sure the water is completely boiling. Okay, after that, the COGON glass undergone alkaline process treatment. First, when the water was boiling, the sodium hydroxide were put inside. Then stir with stick to make sure the sodium hydroxide dissolved in the water. Let the water boiling for 30 minutes and shut off the fire. Left the COGON glass inside closed container for 12 hours. After 12 hours, rinse it with distilled water to neutralize the remaining alkali. And lastly, dry the COGON glass directly under the sun to remove the moisture. Okay, this is the preparation of the sample. Okay, the fibers have been weighed in to make sample for COGON glass fiber. The COGON glass fiber sound absorption samples were formulated with variance in volume, length and in thickness. Fiber net casing are used in the making of COGON glass sample. Okay, this is the example picture of COGON glass fiber that is fully extract and then will weight fiber net casing. Okay, next go to distribution of the sample. Okay, there are 6 sample that was construct in this research with same density, which is 154.04 kilogram per meter cube. The sample of thickness is difference from 10 mm to 60 mm. The mass also difference. Okay, the mass different because to make sure the density remain the same. Okay, the method used to measure the sound absorption coefficient is Fayden tube will be used to measure the sound absorption coefficient of the COGON glass samples. Okay, next I'm going to talk about the result and discussion. Okay, first is about the effect of thickness. In the effect of thickness, the density of the sample is remain constant, which is 154.07 kg per meter cube, while the thickness of the sample will be changing from 10 mm until 60 mm. As you can see on the graph, okay, the lowest frequency is 500 Hz and the highest frequency is 4000 Hz. Okay, the lowest thickness is 10 mm and it shows that it only achieves 0.1 absorption coefficient at 500 Hz, while the highest thickness 60 mm shows that it achieves 0.6 at 0.6 absorption coefficient at 500 Hz. Okay, for the sample 10 mm thickness, it achieves sound absorption coefficient 0.5 at the high frequency, which is 4000 Hz, and for the sample 20 mm thickness, the highest absorption coefficient achieved is at 3150 Hz, which is 0.88. It shows that both of the sample are good absorbent at high frequency. Okay, for the sample of 30 mm thickness, it achieves 0.9 sound absorption coefficient at the frequency of 2000 Hz, while the sample thickness for 40 mm it achieves 0.5 absorption coefficient at 800 Hz frequency and reach the peak of sound absorption coefficient 0.93 at frequency 2000 Hz. It shows that when the thickness of the sample increase, the peak of sound absorption coefficient is shifted to lower frequency. Okay, the sample thickness for 50 mm and 60 mm show that at frequency of 500 Hz, both of the sample are good absorbent as the sound absorption coefficient are more than 0.5, and both of the sample achieve the peak sound absorption, which is 0.9 at frequency of 150 1500 Hz. From the graph, it can be said that the sample that achieve the sound absorption coefficient more than 0.5 is considered as a good absorption coefficient. Okay, next is about the effect of density. Okay, in the effect of density, the thickness of the sample is remain the same, which is 40 mm, and the density will be changing. The 40 mm sample is chosen because the sample is not too good and not too bad. Okay, from the graph, at frequency of 500 Hz, the absorption coefficient increasing as the density of the fiber increase. Sample 1 with density of 100.56 kg per meter cube reach 0.5 absorption coefficient at frequency of 1250 Hz. While sample 2 with the density of 127.31 kg per meter cube reach 0.5 absorption coefficient at frequency of 1000 Hz. Both of the sample achieve the peak of absorption coefficient at frequency of 2000 Hz. With sample 1 is 0.8 while sample 2 with 0.9 absorption coefficient. The peak absorption coefficient for sample 3 with density of 154.04 kg per meter cube at the frequency range between 1500 Hz and 2000 Hz. It shows that the ability of the fiber to absorb sound energy increase as the density of the fiber increasing. For sample 5 and 6, it achieve good sound absorption at lower frequency with 0.5 absorption coefficient. Sample 5 with density of 180.79 kg per meter cube reach the peak at frequency of 1600 Hz with 0.9 absorption coefficient. Sample 6 with density of 207.54 kg per meter cube also reach the peak with 0.9 absorption coefficient at the frequency of 1600 Hz. Okay, both of the sample can be used within low or high frequency as sound absorbent, as it shows that the sample are above 0.5 at the high frequency. Furthermore, increasing the size of thickness of the fiber will lead to the increasing the porosity result, which increasing the stiffness of the fiber between the sound energy. Therefore, more sound energy will absorb and store. Okay, next I would like to talk about effect of fabric. Okay, in the effect of fabric, the 40 mm thickness sample with the same density of 154.07 kg per meter cube is added with fabric to test the sound absorption coefficient of the COGON glass fibers. Okay, the fabric will put in front of the sample and at the back of the sample. Okay, from the graph, both of the sample shows that it achieve a good absorption coefficient, which is 0.5 between 500 Hz and 1000 Hz. But the sample with fabric showed that the sample is more better. This is happened due to the absence of the fabric that were applied at the front and the back of the sample. Both of the sample achieve the peak of the absorption coefficient, which is 0.9, but the sample with fabric achieve at the frequency 1500 Hz, while 1600 Hz for the sample with no fabric. Okay, the absorption coefficient for high frequency also showed that the sample with fabric are more greater compared to the sample with no fabric. Enlarging the sample thickness contribute the loss of sound energy. Therefore, the absence of fabric onto the sample also does affect and influence the sound absorption coefficient for the samples. Next is about the effect of a air gap. In the effect of the air gap, okay, the air gap between the sample and the wall behind is also a factor that can affect the sound absorption coefficient. In this study, the reason of air gap was introduced at the behind of the sample. Okay, in this effect of air gap, the same sample with the density of 154.07 kg per meter cube and 50 mm thickness is used. Okay, as shown in the graph. Okay, the sound absorption coefficient of COGON glass fiber sample with different length of air gap, 10 mm and 20 mm air gap. Okay, the setup of the sample with air gap behind enhancing the sound absorption coefficient at lower frequency. The space with 10 mm air gap achieves 0.6, while 20 mm air gap achieves 0.7 absorption coefficient at the frequency of 500 Hz. The sound energy inside the impedance tube passes through the fibers and directly to the wall and then circulates in the air gap before reflected back the sound energy to the fiber. The more space between the wall and the sample will contribute to more air particles vibrate and dissipate the sound energy. From the graph, the sample with no air gap reached the peak at the frequency of 2000 Hz with 0.9 absorption coefficient compared to both of the sample with air gap reached the peak at 1600 Hz. This is because the sound energy passed through the fiber and directly to the wall and reflect back towards the fibers where there is no air gap behind the sample. For the higher frequency, which is between 3000 Hz and 4000 Hz, both of the sample with a gap of 10 mm and 20 mm air gap shows a good sound absorption coefficient. Therefore, instead of using a thicker sample, this method can save a lot of amount fiber used to fabricate a panel, which can produce a light panel. Next is about the comparison with synthetic fiber. Okay, in this comparison, rock wool fiber is used to compare between with the COGON grass. Okay, the thickness that are used to compare is for 40 mm thickness. Okay, the 40 mm sample thickness of COGON grass and fiber and rock wool fiber is carried out to test the comparison absorption coefficient. From the result graph shown, it shows that both of the sample are good absorption material between the frequency of 1000 Hz and 4000 Hz as the absorption coefficient over than 0.5 absorption coefficient. Okay, COGON grass fiber reached the peak absorption coefficient at 2000 Hz frequency with 0.93, while rock wool fiber reached the peak higher frequency, which is 3150 Hz frequency with absorption coefficient 0.8. This proves that COGON grass fiber are better sound absorption material at 2000 Hz frequency compared to rock wool fiber, but both of the sample are still accepted as a good absorption material. Okay, as a conclusion, the COGON grass fiber is successfully extracted through several processes such as boiling process, alkaline treatment process, and finally sun-dried process. The sample of the COGON grass are also successfully done with various thickness and densities. The effect of thickness, density, fabric, and air gap give positive increment in sound absorption coefficient. The result shows that the absorption coefficient are good for COGON grass fiber and has a potential in sound absorbing materials. The limitation result that could not be achieved are the graph pattern are not smooth compared to previous research due to no binder and compression process. My research in this research, I did not use binder and also no compression process for the sample preparation. Okay, lastly is recommendation about this research. Okay, further environmental tests are needed such as fire retardant, fungal growth, humidity and thermal conductivity tests, which are of interest in the extension of this current work in order to completely confirm the effectiveness of COGON grass fiber in practice. The suitable diameter and length of fiber are also need to be studied in order to get a better result in sound absorption coefficient. Okay, it also possible to correlate experimental work with some established theoretical models in order to make sure the effectiveness of COGON grass fibers as an alternative acoustic materials. Okay, that's all from me. Thank you.